Love me tender, love me sweet.
Wow.
Okay, good. We'll start this way. This time it really does give me a great pleasure to introduce Inbal, that is going to tell us about fairness in decisions under limited resources.
Okay, thank you, everyone. And I want to start by please ask questions. Because first, I don't think I made a really long talk, and I tend to go really fast when no one interrupts me.
Unlike me, that I tend to.
So really, please ask questions. I'll be really happy if you interrupt me at any point. And I'm going to also start with a similar disclaimer to Omar's, that I am theoretical CS. I'm going to present a specific work that is a theoretical CS work. It is inspired by a problem that happens in computational healthcare, but it is not a computational healthcare work. So I'm going to do motivation, and then I'm going to present a problem that we're trying to solve, and then to say what we're going to do about it, which is, if sort of continuing Omar's talk, to give more options, more fairness definitions, to have a richer language to have our values in a mathematical way in this specific setting of very limited resources. So background, we have many medical algorithms that are algorithms. They're doing a lot of different tasks. They might do image processing. And the type of decisions I'm going to focus in this talk is exactly not the example that was in Omar's talk, but an example that is like resource allocation, connected to resource allocation. So we're not trying to do pro and con of, say, doing an operation or a medical or decide what is best for some person, but rather we have some specialists. There are, 100 people that this specialist can see. And we need to decide who are these 100 patients, where the assumption is that there is never a damage, like we never harm someone by, say, sending this person to see a specialist if eventually the person there is a false, like he doesn't need it, yeah?
Is that just a mathematical convenience, or does that have actual effects on the?
It has actual effects.
Okay, so if that assumption were not the case, then the results might differ.
Like, it would not make sense to apply
Gotcha.
this in a setting where you actually might do harm because you have different considerations.
Okay.
So sort of the baseline of what we care about in this work is that we're never doing any harm, but we're trying to understand who are the people that we need to get this resource the most. So there are many examples that at least broadly can be described as this way in the medical settings, like beds in hospital or in intensive care or medical MRI images, stuff that are not supposed to cause harm by themselves, but are very expensive and very limited. So this is sort of the broad medical example in mind. And this is, thank you to Omar for the previous talk. I am going to model the decision as two steps, where one of them is risk estimation and the second one is decision, assuming the risk estimation is done properly. And when I mean properly, I mean if this P is multi-calibrated with respect to a rich enough class of functions, then I assume it describes correctly, like the best I can assume. And we're sort of going to assume the first part correctly describes the probabilities, and then the second part is we want to allocate resources assuming these P's are calibrated and sort of they mean the best thing we can. And sort of a distinction I want to make sure is clear is that there is a really large difference here between the two steps, in the sense that the first one is per person. Like, if I find out some more information and I change the probability of this person, it has absolutely no effect on the risk prediction on any other person. Like, if I now know that her mother had cancer, it would affect her risk, but it would not affect anyone else's risk score. But the second part, if there is only 10 people that can go to MRI, and now this person's risk go up, and she goes to MRI, then someone else can't go anymore. So sort of what I care about in these two steps is like this is an independent step, like it's a personalized one in a sense. And the second one, because of, I assume the resources are very limited, there has to be some dependency. Like if we change the value, if we change our decision on one person, we actually change a decision or at least one more person. So this is a formal setting. Again, I assume a distribution over people, that I have a known patient's data. There is some unknown value I want to predict. But then I assume there is a second step that takes the prediction and all of what I care about, that will be not only prediction, and make some decision, where for the simplicity of this talk, this decision is binary. It can actually be randomized. And I assume that we have a strict limited resources. It's going to be some small number C. We want to fill it all because we assume we only gain from this intervention, so we have no reason not to fill it all. And we want to do it in the best way. What is the best way? So I don't know if it's surprising or not, but in this specific setting of a resource that's limited and we want to, it has no harm, there is actually sort of a single, for any kind of binary loss that's reasonable that we're trying to minimize, or if we're just trying to maximize like how many people we allocate that really have value 1, this is all converges to the same hypothesis. So sort of what we have is we're trying to catch as many of the y equals 1 people.
Can I ask, maybe it's not the right time to ask, but while you are talking, I'm thinking on examples, and in case this is how I think. So for example, in this calculation or estimation, does the clinician include, let's say, a psychological burden? I mean, if you have a woman who is 25 and you say your risk to breast cancer is such and such, or because, as the example you just gave or so, but that by itself is
I agree that the assumption of saying sending to a specialist does no harm is a simplification to some extent. And also that you can do it in a sensitive way, not telling someone you have a huge risk, go, but just refer to a specialist. But it is a simplification that is taken here. Like I really assume no harm, even though I agree in real life it might not model perfectly.
We discussed about yesterday about autism, and much of the discussion was what parents will do if they know or do not know, and so on. So it's a big
this is a simplified
making.
It's a simplified assumption that the refer to a specialist has no harm does not necessarily hold in all cases.
So I have a question about the expectation of f of x equals c. What is c supposed to represent here? Is it the
like of your capacity, like number of say beds in ICU or number of specialist appointments you can have?
Yeah, so the reason I ask is because the way it's written here, I think it's more like it's like a fractional.
Yeah, it's a fractional,
right? But that makes a big difference because then a fractional, the amount of capacity you have goes up with your data set size.
Yes. Yeah, I assume this is like some fraction that we know.
Okay, so you're assuming that it's fractional, not like you have a capacity of k, where k is independent of your data set size, which means then the fraction would go to 0.
In what I'm going to do, it actually doesn't matter, I think.
All right.
But yeah.
Yeah.
Okay, so anyway, what I'm trying to say is that first of all, what we say the best way is not really ambiguous here. So we're just trying to catch as many of the y equals 1 we can. So that's the setting. Now, what do I mean by information gaps? So I said we model the process by 2 steps, and the reason I'm modeling the process this way is that then I have a risk estimation part that I can talk about how good the risk estimation. So really the issue that can happen is that, okay, suppose P is calibrated and it's multi-calibrated and it's great, but there is some set that it doesn't distinguish very well. So it can say 0.3 on the entire set. It is calibrated, about 1 out of 3 really has this condition, but it's not helpful in a sense. It doesn't have a good enough distinction between like the high risk and the low risk. So what I really mean is that we can recognize more high-risk individuals in one group comparing to the other. And what I want to say is that this is something that can happen, and it's not necessarily meaning that all the people in S2 have low risk. It just means that we don't know which of them might have high risk. I mean, even if we're predicting, say, a future, so like who will have a heart attack, it does not necessarily mean that all the low-risk patients are actually low risk. It just means we might not know the relevant features. And sort of if now we have more information, this doesn't mean that this person is suddenly in a higher risk for a heart attack, just that someone put a new feature in our feature set. So this is like an assumption about the problem. I assume here that we have information gap that leads to this distinction, and not that some group does not have any high-risk patients. So, because the work is going to be theoretical, this is sort of a data assumption that I'm making here. So this is the setting I care about. But still, I want to say that this thing happens. Like, we do know that we have populations on which we really have information gaps. Like, if we have populations that are immigrants, they don't have any documented family history, or in the US, where there is no health care for everyone, they might not have family history or their own history. Sometimes we know less. Like, maybe in autism, we can recognize less well females, because we know less on the general or because of any other reason. And also, people behave differently. Some people come more to the doctor. They have more data on them. So at least in some cases, this assumption that there are some high-risk people, but we just don't know where they are, but we know also which populations we are missing the people. Like, we know which people are immigrants and have no medical history. We don't know who the high risk of them are, but we still know that we are missing them in this population. So sort of this is the like general framework that I want to discuss. And then, okay, so what is it? First of all, do we even have a problem here? So what happens normally? Like, we have a predictor, we have a really, really strong capacity limit. We will take the highest risk people, and we will show them, send them to a specialist, or send them to some test or something. So what will happen? This is synthetic data completely, but this is just two normal distributions where one variance is larger than the other. So if this is our predictor, like this P of X, and the blue one is one population, and the red one is a different population, then basically no one from S2 is going to get tested at all. Because for example, if something is hereditary and we don't have anyone in the family diagnosed, then the highest risk patients are not going to show up because they're not there. We don't know who their family are. Now, it doesn't happen all the time, but it happens if we have a large information gap and a strong capacity limit. If we could test everyone, we wouldn't have any problem. If we had no information gap, we also wouldn't have any problem. But such setting happened, like information, medical history gaps. Yeah?
Sorry, and feel free to cut me off. So is information gap here increasing or decreasing variance? Because I feel like you can make an argument for either.
Increasing.
Way. Okay, it's increasing. Right.
Yes.
And
like more information, meaning larger variance. Like you can have more high-risk people in this population.
I feel like that's...
like imagine zero variance. Let's take it to extreme. P of X is always the same on the entire population. Then you don't have any information on it.
That's sort of an implicit assumption about how we would interpret uncertainty in practice, right? Like, if I have no features about a patient, I am maximally uncertain
Yes.
about what their diagnosis is.
Right.
Not minimally uncertain.
So I'm assuming P of X is like a risk for a specific condition. Like if you have, I don't know, suppose some person came to you and you ask, what's this person's risk for having a heart attack in the next 10 years? But you know nothing about this person. You would just say the average in the US population or something.
Maybe, or I would pick a number randomly from an uncertain distribution that
Yes,
in
you can
expectation
also-
is the prevalence in the US population.
Yes, I suppose you can do that. I'm assuming you're not doing that.
Okay.
Okay, yes. I'm assuming that you're not trying to like sort of artificially generate larger variance by just answering random,
Well,
like increasing the randomness of your predictor.
I actually think it's not artificial, it's very reasonable, because again, you know nothing about the person, so you should be maximally uncertain about their diagnosis. Like saying their aggregate risk does not imply that uncertainty in some sense. But regardless, I see your point. You're assuming
I'm
that's
pretty sure
homogeneous.
existing medical predictors do not do that.
That I agree with. That is fair. But my second question is, so you're assuming equal mean here for these in the synthetic
For
data,
these
obviously.
distributions are actually not exactly equal mean, but more or less,
More or
yes.
less. So you said if you have no information gap, there's no problem.
Yes.
Are you saying that suppose the means were very different, but no information gap? Is it appropriate that you potentially are only choosing from one group because they have higher P of X? Is that something you're asserting?
There are going to be differences between the means in like some number of slides in the future. But generally, sort of the classic example I have in my head is at least similar means, like that your actual issue comes from the information gap and doesn't come from the difference from different base rates. Yes, but there is going to be at least the definition of equal opportunity that Omar mentioned is going to act differently on different means. So first of all, maybe that's good. So that's one option. Like this is now, like we said before, fairness definitions needs to they incorporate our values. So a very utilitarian point of view, or just saying, okay, we want to save as many people as possible, we're going to take the highest risk. And we do not care about the fact that we're completely missing some population. And in some cases, I am pretty sure people will decide that, because if it's a medical case and it's like beds in the ICU, doing anything except that will actually cause a higher death rate. So this is one option, and I'm not saying this is necessarily the wrong thing to do in all settings. But there might be some settings where we don't want it to happen, because some very weird stuff can happen when we only threshold the risk and we have information gap. One of them is, suppose the groups are looking like this. This is a really completely made up and ridiculous distribution. But still, in this one, we're going to take 100% from S1 if this is our capacity, even though the difference is actually tiny. Just because we didn't consider the entire population, we just did a max, like a thresholding. And normally the group we know less of are the most vulnerable people as is. And definitely, if the gap is because we don't know how to diagnose some group, we're not getting any new information here, because we're not continuing to not diagnose this group. So at least in other settings, this is not what we want to do. So, okay, we want to do something else. What do we actually want? So I go back. There is no fair action in any setting. Probably what people or experts are going to consider fair for beds in ICU and for appointments for specialists is likely not to be the same. But what do we need if we're trying to say, okay, we need to decide on what's fair to do here? We need some definition. Now, what's happening right now, probably, is that every person, a PCP has a set of patients, and they do some allocation. And they might take the information gap into account, and they might not take it. And each person will have a different decision. But if we're going to now have a predictor, we're going to enforce our decision globally. Like, whatever we decide, this policy is going to affect everyone. So sort of, we're creating here something, like if we replace many human decisions by one algorithm, there is a possibility that we were going to do harm to some population that previously people sort of manually said, that doesn't make sense, I'm not sending anyone from some population. But if we want to do something, then it means we need some sort of a mathematical definition. So it should be a formal definition we can enforce. And we also want to apply it in many different settings, because if we have different distributions of our population, it means our definition needs to make sense even for one decision, like appointment to specialists, for the very different distribution, because we're not going to send people all across the US for a specialist meeting. So each area is going to have its own baseline. So we want something that would apply in many different settings. So I'm going to start by saying, what happens if we just take a standard group fairness definition and apply them? The first one, the same thing Omar mentioned, we just treat the groups exactly the same. We take same fraction of every group, like we say, women are 50% of the population, 50% of the autism specialist meeting should be 2 girls. Doesn't matter what the base rate we think, it doesn't matter what we think about the actual people. So that works. But it's very non-adaptive. Like, if we have a slightly different rate, or we have a very large rate, that would act exactly the same. It is very robust in the sense that you're never going to get something very weird as a result. But it also doesn't do anything which we might want to do. It doesn't trade off like utility and fairness. You just have a block decision. OK, can we do something else? So another definition that Omar already mentioned is that we're sort of saying, OK, suppose we have a really different base rates. We're looking on the actual people that have a positive value, that have y equals 1. And we want to catch the same fraction of them from both groups. This definition normally, that is not in the setting of extreme information gaps, is sort of less strict than demographic parity. It gives a slightly higher rate for those we know less of. Here, it acts really weird. It could, first of all, it's by far stricter. Like in any kind of a tail-bound setting, it gives more resources to the group we know less of. And it can go to extreme. Like, if you don't know anything about the people in S2, you need to test them all. So this is something we might not want to do. So what do we want to do? What we did in this work was to say, OK, so we're missing here something, like the existing definition don't grasp what we want. But there is a lot of literature in computer science, not in like machine learning, that is a resource allocation definition, resource allocation perspective. So what happens in resource allocation? We have some shared resource. We have all these agents. Maybe this is, I don't know, water, electricity, something. And each of them has some usage. Like, what would happen if you give me so much water? What will I do with them? And they have like a utility function for this thing. And then in resource allocation, the goal is to distribute this like shared resource in a fair way that maximizes like the global utility. So a very standard definition in resource allocation is max-min fairness. What is max-min fairness? Sort of, ideally, we need the least happy people to be the most happy. Like, if previously this agent was really unhappy, we can give it a lot more resources, even if it makes them slightly more happy. Because what we care about is like the least happy person. This is the least happy agent is what we're aiming to increase. Another definition that's used is to do the multiplicity of all of the utilities. The idea behind this is that this is sort of prevent any UI from going to 0, but it is not as strict as like trying to focus only on the least happy people. So this is sort of a balance. So what we did was to say, okay, we have these two definitions. We want to migrate them to like a prediction setting. So what do we need to do? So we need to say, okay, which are the agents? Agents are the group. That was pretty easy in this idea. But we need a utility function. And this is a choice here. Like, what do we say the utility of the group? So this is a choice we made. Like, how many people we say tested that were actually positive. But this is not completely, we also need to do something else for proportional fairness, which I'm not going to focus. But this is an important choice. Like, this is a value choice in a set, in a way. We could have chosen the true positive rate. We could have conditioned on y equals 1. We would have gotten a different set of fairness definitions here. We could have done some sort of a loss equalization. There are works doing some sort of loss equalizations. The reason we chose this specific definition is because for most of the use cases we had in mind, we care about the number of people from the group we found, not necessarily the ratio. But this is sort of, and it doesn't equal any of the other definitions. So this is like a sort of a incorporating choice we made. And I sort of want to stop in this point to do a detour and say, which I think sort of connects to the lecture earlier today, that these kind of choices are often sort of run away. And we don't notice that we're doing them, but they're important. So like we ignore them. You sort of say, you know, we need to equal utility. And you don't necessarily think about what is the utility we really care about. Or like I said earlier, we choose a model, a set of hypotheses. This affects the fairness. We choose how do we treat missing data. So there are tons of these choices that we made anytime that we're using an algorithm. And all of these choices, they affect both the accuracy, but they affect the fairness, and in many cases, they affect the fairness in a way we don't see. Like, this is just some subset of what we need to choose. We need to choose a loss function. It might be L2 loss, but why would specifically L2 loss be the one we care about? If we have missing data, like I said, we need to fill in the missing data. If we do some reweighting normalization, which is a hypothesis class. So we have a lot of these choices, and they exist sort of everywhere. And we don't necessarily know how they affect fairness when we choose them or how they affect accuracy. But what I'm trying to say is that sort of any algorithm we have incorporates our opinions in some way. And because this work is theoretical, I didn't have any data to decide anything on. But sort of this is, in the idea of deciding what's our global utility, there was no difference in anything we choose, just because we have full utilization. But in the pair group utility, we did have a difference. So any kind of choice resulted in a different definition. So sort of what is just a detour to say this stuff really matters, and they tend to get forgotten or ignored or hidden in some way. And I wanted to sort of put them here and say these choices are important. So this is a detour. What we chose was sort of f equals 1, y equals 1 for the pair group utility.
So just to clarify, you are assuming that the cost of resource allocation to the subpopulations or groups is the same?
Yeah, I assume, like, say I have a specialist appointment, and it doesn't cost me more to fill it up in any different person from any group. But I can't, like, find a new specialist for like this resource is completely limited I don't have any more control over it.
But normally, such a cost would not be the same, right? The cost of providing, say, a particular specialization in a remote village will be more than in a city, for instance. And
Yeah, it's more like per specialist, you have a city, you have many different populations. Who are you sending?
And of course, this would lead to different optimization frameworks.
Completely, and there actually is a work, which I don't remember by whom, that specifically discussed location of different, like discuss exactly your question, like how to locate the specialist to make it fair. So it's sort of a complementary work, and if you care, I can look it up. I don't remember what it is right now, but definitely people are looking at.
In the 1950s, there was work by a Soviet economist, Kantarovich, which got a Nobel Prize, which he assumed that the cost of resource allocations are going to be different.
Yeah, that's. So there are very different variants of how you use it, and sort of in this model, I assume it's like a single center, and I ask who do I send to it, rather than where should I put my center. But yeah, there are a lot of variants of, and also a lot of resource allocation variants from, I don't know, memory in your, this is what Eitan that I was doing this work with always had RAM, and which process gets your RAM. And there are a lot of variants, like resource allocation papers are in a lot of different settings, including facility allocation.
Sorry, you can keep, no, I just, okay. So apologies, I may be missing something obvious here, but so why is this maximizing the sensitivity, or why is this maximizing the recall and not the precision?
They all come to be the same. That's that in the specific subset of we fill up all of our slots, and we have a predictor. Everything here goes down to you do a threshold and put all of the highest ones in. Like if you don't have any fairness, this is what I'm saying. This is like my what's the maximal utility. So they all comes down to be the same. You take your highest risk people, you give them all the F equals 1, and that's it. But sort of, because once you only have a single population and you fill up, you know you have to fill up your entire slot, then your decision is basically trivial.
Yeah, but I guess my question is, so as that assumption becomes less true, then what you care about in some sense is more precision than recall, right? Because it's top of list that you're optimizing for.
So in the entire talk, I sort of focus only on the second part. So I don't really have I assume my predictor is someone made a really good multi-calibrated predictor.
Okay, so you assume your predictor is very good.
I
so
assume my predictor,
really
it's not necessarily very good. I mean, it's not very good, but I don't know how to improve it.
Okay.
That would be
my,
my,
yeah. All right, in that case, I have no objection. Yeah.
Yes, so this is like my underlying, that was my underlying assumption. I don't know how to improve it.
Okay.
And then my question is, okay, what do I do if I can't improve it? Do I allocate, and can we use these definitions better? So one thing we notice is that equal opportunity and max mean fairness are actually very similar. Sort of, if we have equal base rates, then in this definition, they're and a rich enough class of functions, they're identical. If we would have defined the utility as the rate, then they would be identical regardless of your base rate. So they're basically the same. So I think this was sort of folklore, now in different settings. Unclear, couldn't find a very precise definition everywhere, but in this specific setting, they're the same. So what they do is basically they equalize utility. They're saying how many of the y equals 1 in each group we found. For unequal base rates, this is the distinction I had. Equal opportunity gives more resources to the group that has more y equals 1, regardless of how much information you have on it. But two of these definitions they're very unstable in this setting. So first of all, they're always stricter than demographic parity. And when I say always, I mean as long as we have we are in the tail. As long as one P specifically dominates the other group P, they will always be stricter than demographic parity. And also they can go really weird. Like, if, again, it's like a completely simplified example, but suppose you know nothing on S2. Really nothing. There are some people, but I have no idea who they are. Basically, what this definition means is you allocate everything to S2. Because you're trying to find the same number of people, and you don't know anything on S2. So this is too strict for any kind of practical purpose, but also it's sort of unstable. Like, even if it works well for some population, we cannot be sure to, just use it widely because it will act weird in different populations. So for proportional fairness, what we showed is that you can sort of break it up into a fairness term and a utility term. So this is implicit, like you're not actually trying to do it. What you're trying to do is to maximize this multiplication, but this is the same as doing fairness regularization with a multiplicative regularization, which is not the standard way to do regularization. But, and what it means is two things. First of all, it's always less strict than max min fairness or equal opportunity. It will never, it will always give more weight to utility. Because sort of equal opportunity is like if you would ignore this log term. But we show something else. We show that this means we are always guaranteed half of the best utility we could get. Like if we would be totally utilitarian, we would catch 50 people. If we require proportional fairness, we're at least promised to catch 25 people. Doesn't matter anything about the underlying distributions. Because sort of this extra thing would force you to put enough weight on your total utility.
Can you play with this definition, give more weight on this term and get any balance that you want?
So I didn't do it yet. That was in my to-do list, but unfortunately we had an ICMA deadline, so I don't know. And I'm also not sure what happens in extreme cases, what at least was a little bit annoying for me, this goes towards demographic parity. Like in the case, in a really extreme, in the really extreme example, you're likely to get 50, you really are likely to get exactly half. So it would be good to figure out a way to relax it even for the extreme cases, because it doesn't give maybe even in the extreme cases, we don't want to converge to demographic parity. But in a non-extreme cases, it gives a different balance.
But I can imagine either, if we go back to the previous slide, either working with this equation and playing with the
with the log factor. Yeah.
Or alternatively, introducing into the product. I mean, having in the product also terms that are only about having U total to some power.
Yes. So there is I think a power is actually better because multiplication doesn't do much because this is about the rate.
Right.
Yes.
Yeah. Interesting.
Sorry, just so I understand this. So first off, is this equation is exact, or is this sort of?
This is exact.
Okay. Secondly, so U total here is the total utility across all of the.
Addition, yeah. If you just sum them up.
And in the fairness setting, the utility is the true positives.
It's a true positive,
Number.
not normal number,
Number
not
of true
normalized.
positives.
Yes.
Okay, so U total there is the number of total true positives.
Yes, in all of the.
Yeah, across
groups.
all here.
Yes.
And then the KL divergence term is with the. What's the D max min is?
Okay.
And DF, yeah.
Yes, this is why I didn't define purple on the slide because I was trying to make it not so mathematical. It's like the distribution of true positive count per group. Like it's actually only you have a value for any group. So in the case of two groups, this is a distribution over two values, but actually this is true regardless your number of groups.
And what's D? So that's D max min.
And f is your function, right? This is like
it's how many your function would select.
how many your function would select.
If you were to use it naively in some sense.
Like if you would use your f, like for every f you have your value, but the goal is to maximize this value.
I see. So you're maximizing f subject to this.
Yeah, I'm maximizing f subject to this thing when u total also depends on f. So.
And so does d max min then.
Yeah, no, d max min is what max min would give you. Like max min is a specific solution.
Okay, so d max min is what max. I see. Okay.
Yeah.
So then, to Omar's question a moment ago, you could also change that. You could, because basically what this is saying is that you have some sort of minimum term that you need to get, and then you're trying to otherwise approximate the max min distribution.
It's a balance. It's actually a really equal balance.
Right. So you could say, oh, I don't actually want to approximate max min. I want to approximate a different distribution.
You could, and actually we did it at some point.
Oh, okay.
But it's not in the slide. But yes. So what I wanted to say is actually, without getting technical, this is sort of a halfway balance between fairness and utility. In terms of it puts like. Basically, we break it into two equal parts. And in general, it's a weird balance. Like in general, fairness regularization that's multiplicative and not additive is not something which is standardly used. And so yeah, we're always promised half of the total utility. I am saying this is only in this specific setting where we post-process a predictor. It's not true for the general definition in the utility setting. Like in the original utility setting, it doesn't hold. But yeah, so this is what we're doing. So this means this definition is more stable in the sense of you can send it and you're sure that at least even in the most extreme case, you get half of your total utility. So this is something that we like. Now, another thing we did was to say, okay, equal opportunity acts really strange in some sense. And then we thought maybe we can fix it. So the way we fixed it, or like actually generalized it to a limited resource setting, is to say, okay, what we used to do is to say we want to catch the same fraction over y equals 1 in both groups. But really, if we have really no information on S2, we will never catch all of the y equals 1 in S2. We don't know who they are. So what we said is, what happens if we give all of our possible resources to S2? We would catch some fraction over y equals 1. Not everyone. So suppose we have two groups. We decide we only test women. Then we have some number of women we would find out. And then what would happen if we only test men? We would have some sort of a y equals 1 that we would find out. And use this amount of y equals 1 as our baseline, instead of all of the y equals 1 in the entire population. And sort of the idea here was to say that those that we can't reach, we anyway can't reach. They're completely out of, even if we had only one group and we allocate all of our resources to this group, we would still miss these people. So we can not take them into account when we think about what is a fair allocation. If we do this normalization, then we get sort of a similar promise. Like we are promised at least half of the total, like maximal utility you can have. They're acting strangely similar in simulations, but I'm not sure what the real connection, mathematical connection between them. They don't seem similar mathematically in any sense. So in this, like, I'm not exactly sure what's going on with these specific relations, but this is a relaxation that works. It is weird if we have really small groups. Like you just can test the entire group, so it doesn't change much. But if you have like pretty large groups, then this gives you sort of, it takes into account that you can't reach everyone. So basically, this is the new definition, and this is most of what I wanted to say. So as a summary, there are two things I want to say. One of them is that this is a problem that we can see just because of information gaps. Like this is sort of a hidden problem in this sense, that when you apply a model, you don't think, maybe this population doesn't have as much family history, and so we're going to miss it. These kind of problems can sort of hide in your data. So I wanted to say that this is something that can happen. And that one of the ways to do it is to say, OK, if we notice we have a problem, we can enforce fairness definition. And then we saw that existing definitions sort of do not really work well in this setting. So we borrowed definitions from resource allocation that was, because this is actually a form of resource allocation. Now, this is, again, a theoretical work, sort of showing equivalence or bounds on different definitions. And if we're in an audience that's more applied and more medical, I think there are many open questions and discussions that can be related to it. First of all is, what do we actually, how does predictors of different conditions on the entire population look like? Because in most different conditions can be extremely different forms of distributions. And then any medical condition, all these definitions act differently if you have these different distributions. And I'm not really sure how existing medical predictors look like. And how large are existing information gaps? My sort of largest one I can think of is hereditary conditions and no family history, but there might be other reasons for having large information gaps. And sort of more connected to like a discussion question and more connected to what Omar was saying, is that the right thing to do in these types of questions is really complex. Sort of, we said, OK, we give one more option. But in general, in very limited resources setting, it's hard because every decision for fairness comes on the expense of your total number of people you can catch. So a couple of days ago in New York, there was a survey question about sort of a related question of ads, and would you pay more to reach some population that we miss? And most people said yes. But this question was very most people said, yeah, we agree to reach less people total if we reach some vulnerable population with ads about, I think, food stamps. But this definition, you don't feel like you're coming on the direct expense, like, say, beds in ICU or something which is medically and critical. So what are the right values that we can sort of, we might like to incorporate as a fairness definition is something we added one more, but I'm not sure we have the right balance, or I'm pretty sure this is still might be too strict for what practical cases people might want to say. So this is a general discussion, and I'll be happy for questions.
Sorry. So first off, I just want to say I think this is really interesting, and there are lots of large information gaps outside of genetics and contexts like this, where you're there you're almost talking about a I recognize you're saying we don't know family history, so that's why you don't have the information. But even in a setting where a patient just hasn't had their genome sequenced, or even where we just don't know for a certain two patients have the same disease, but one is from a single gene in randomization, the other is polytype risk or something. We don't know the same things, right? But even outside, and that may be a bad example genetically. But just talking about EHR data, especially in urgent care settings, lots of people come in and you have no history, and
zero.
Then they may not be able to. They may not be mentally fully well, and may not be able to communicate to you their own history, and things like this. And so the care.
So that's really a setting of average. This is an average person with a heart attack, zero.
Yeah, and the information gap there is clearly correlated with other factors that we may want to control for, or not control for, but we may want to balance fairness over, right? So I think it's a critical setting. That said, I actually think that my statement at the beginning about a random predictor or something, I think it's actually much less crazy than it sounds. And I would challenge that it might be a very productive way to look at the information gap. Because if you think about this in a Bayesian sense, you say, oh, I don't know the probability that any patient X will have, but I have some prior distribution, not over their probabilities, like a beta distribution or something, right? The more you observe, the peakier that distribution gets. The less you observe, the more uncertain it is.
While I agree it might be the right thing to do mathematically, I think people would very strongly object to you using a random way of putting people in ICU.
I'm not suggesting that they wouldn't, but even if it's not something that you would actually implement, it may explain different decision choices.
It may result. It actually might even coincide with existing definition, like the way you do your Bayesian.
You can do A/B testing on people that.
No, I mean that's immediately you get your experiment does not pass IRB muster.
Yeah,
But in particular, something I want to highlight is you had at one point the S1, S2, 0.29, 0.3, and you said, oh, we assign everything to S2, even though they're basically the same. As soon as you imagine these being
that would completely go away. I agree. Yeah, and I think the assumption that we're even thresholding, which I think Eitan said is going to speak tomorrow about different approaches, the assumption we're thresholding is also by itself sort of a design choice that I've made, because my assumption is this is what people are actually doing. Like, I don't know if you, like, what would people do in real life? They would probably threshold, would not do some random function over all the people that have a pretty high risk.
Well, I mean,
I'm not saying this approach might not work. I'm just saying, from my understanding, people would threshold and not do randomized decision making.
But you pose at the end this question of, like, how should we balance?
Yeah, this is another approach
like,
to balance. If we have
an information gap, how do we choose? And it seems like in some sense we say, well, the information gap gives me some probability that I think they actually are higher risk versus actually lower risk, and that's a choice, right? And we want to balance that probability.
Yeah, it might give a completely different approach to get either same or different fairness notions. Yeah.
Okay, I'll ask. One is, I wonder if there is any way to set, if you assume some cost for gathering information.
Like exploration, exploitation.
Perhaps you can set up
internal.
Set up the definition to create the right level of incentives to gather whatever reasonable information it is. So not to go crazy and gather more information that's unreasonable, but I mean, these things are not static. You can,
of course, although
you can have an interview with a longer interview with a patient that doesn't have history or something. So the question is, can you?
I think
if you make some economic assumptions on the cost of gathering data, perhaps that it can guide your definition.
I mean, I think it definitely will work in some cases of information gap. I'm pretty sure it won't work in, say, the genetic thing, because probably getting, maybe. Like, it depends on the costs.
Yeah, so you need some to model the cost and so on.
Like, different information gaps would cause an very different cost function to exploration.
I think you are making an implicit distinction between the two types of information gap. So one of them is on the individual level. For example, if you have missing a measurement of a person,
right? That's an easy one to get.
It's not an information gap you are talking about mostly in this talk, because you are referring to information gap, or you have a population where your model is performing or is less accurate, right, or less calibrated.
Not less calibrated. I assumed like everything is perfectly calibrated, but say less distinctive.
Okay. Yeah.
Yeah.
Less
but
variation,
yes. But I think maybe less variance if we assume.
So, but if I can say something.
Yeah, sure.
So, I think that information gap is one problem that causes the one problem that would benefit from your solution. In any case that you have a different distribution of scores or the base optimal prediction for different groups for whatever reason, not necessarily an information gap, maybe that's something intrinsic in the groups, then you will have the same problem. So I think that's more
fairness argument.
It's not necessarily that there is one group where you perform badly. It's two groups that are different.
I think that the reason we focus on information gap is mainly because it's easier to rational fairness. Where you have information gap, you're saying, these are high-risk patients I'm missing, I want to catch them. Whereas if you would argue they have different properties, then there might be, it's unclear that what you might want to do. So it was definitely our choice to be less ambiguous about the reason to use fairness definitions, but yes, it works for any, even if the distribution is intrinsically different. So, I don't know, you're choosing excellent students for some program, and people have different background, and they really have intrinsically different achievement because they don't have the same background or something.
Okay, let's thank So Shafi organized for us an early evening. We were supposed to have another talk later that was